Hello students, this is going to be section 3.3, part 1. This is where we start trying to understand about graphing. Okay, let's have a look at the first question. Here it is. And they've given me a graph, and they want to know, based on the graph in the figure, determine where the derivative is less than 0. Okay, so here is that graph. And the place where the derivative will be less than 0 is wherever the slope of the tangent line is negative. So starting right here, all the way to here, you have the function decreasing. The slope of the tangent line is negative, and then from here on out to infinity, the slope of the tangent line is negative. So it's going to be from -4 all the way to 2, and then union that with 5 to infinity. So it's from -4 to 2, union 5 to infinity. All right, here's a graph. Select all the points at which, so here is a graph of f prime. Select all the points at which this graph has a local minimum. Okay, so here's our picture. Now this is f prime. So wherever f prime is equal to 0, that is where f has local maxima, right? So my candidates, so at these 3 points is where f has local maxima. But to have a local minimum, I have to be decreasing. It has to have a horizontal tangent, and then it has to be increasing. Well, that would mean that if I have some point here where it's going to have a local minimum, then I want f prime to be negative and then switch to positive. So you have a local minimum here, and you have a local minimum here. Because if it's negative, then the function f is decreasing, and then here the function f is increasing, so it had a local minimum at p. So that would be -2 and 2. All right, given the function above, use the first derivative test to find the local extrema. that means for us to take the derivative and set it equal to 0. Okay. So here's our problem. We ought to be able to do this derivative pretty easily. Here we get minus 6x squared minus 30x plus 144. Now I need to factor this derivative. So a negative 6 will factor out of all three of those terms, and I'd be left with x squared plus 5x plus 6 minus 6 times 12. Let's see. So, no, not minus 6 times 12, sorry. So, 2 times 12, that's what I meant. So this would be minus 24. There, now I've got the GCF factored out, so now I can try and factor this part here, since the GCF is 1 on just this part. And it's looking like I'm going to get a 3 and an 8. So there's my factorization. And now what we've learned here is that the critical values are 3 and minus 8. In order for those to be local extrema, it has to change from increasing to decreasing or decreasing to increasing. So let's just check right quick. And we'll do the test point method. So 0 is in here inside of this interval. And if I put a 0 into this function, it would be positive. And because all these roots are unique, then it's just going to alternate back and forth. That means that my function was decreasing and then increasing and then decreasing again. So it has local extrema at minus 8 and 3. Okay, so there was a minimum at minus 8 and a maximum at 3. All right, now we've got another graph. Identify where the derivative is negative given the graph of f in the figure. Well, that's no problem. Here we would just be looking for where the function is decreasing. So here is that function. And it's going to be decreasing everywhere before -3 and everywhere after -1. So that would be from -infinity to -4 union -1 to infinity. I said -4, sorry, I misspoke. You can see that -4 is way over here. I'm talking actually about -3. -3 and -1, that's where it, those are the edges. So this is where it is. That's where f is decreasing. And what that translates to is f prime being negative. All right. For the function below, find the local extrema using the first derivative test. So here's that function. Then r prime would be -6x squared minus 66x minus 108. And I want to factor out the GCF, so I'll factor out a -6, and I'm left with x squared plus 11x plus 18. And then I'll try and factor that leftover quadratic. And I think it would just be a 2 and a 9, x plus 2 and x plus 9. So I'll make my number line drawing for a -2 and a -9, because those are the two values that are going to result in this thing being 0. The -2 would go there, and the -9 can go there, and if either of those happens, I get 0. And then by the test point method, 0 is over here, but I don't ever put my test points on the number line because it makes it cluttered. I can just look at my original function, and if I put a 0 in for x up here, then this term is 0 and this term is 0, and it's negative when x is 0. So it's negative in this interval, and then because these are all unique, it's just going to alternate back and forth. That means that r is decreasing and then increasing and then decreasing again. So it has a minimum at -9 and it has a maximum at -2. All right, here's a graph. And they want us to consider this graph and select all the points at which it has. So this is the graph of f prime. And they want us to find all the points where f has a local maximum. Okay, so if f is going to have a local maximum, then that means that on the number line drawing for f prime, if this is the number line drawing of f prime, then there's going to be some point where it has a local maximum, and for that to happen it would have to be increasing and then decreasing. And that would translate to f prime being positive and then negative, but it would be 0 right here. So that doesn't happen anywhere. That doesn't happen anywhere on this graph of f prime. This is f prime of x. It has a local minimum here at 2. It has a local minimum right there because right at 2, on the left side of 2 it's negative, and then it's 0 right at 2, and then it's positive. That means it was that means f was decreasing and then increasing. Okay, and like right here at -1, it's negative on both sides, but it's 0 right there. So that means that f goes down. It goes flat briefly, just enough to make a horizontal tangent, and then keeps going down some more. So for this graph of f prime, the function f has no local maximum. Identify where f prime is positive given this graph of f. So here's my graph of f. Now f prime is talking about the slope of the tangent, and so it's only going to be positive between here and here, between -6 and -4. Because that's the only interval where the tangent line has a positive slope. That's the only place where the tangent line has a positive slope. So it's from -6 to -4. The graph of f is shown. Where is f prime positive? That's from 2 to 6. It's from right here at 2 to this x value of 6. Everywhere in between, and I said 2, I meant 3. Here, let me draw a picture. So from right here when x is 3 all the way until where x is 6, every point in between has tangent lines with positive slope. So it is between 3 and 6 where f prime is positive. Consider the graph of f prime below. Select all of the points at which f has a local maximum. So in order to have a local maximum, I need f prime to switch from increasing to decreasing, and then it's going to have a place where it's 0. So a local maximum would look like, a local maximum would happen right there at P if it took on the value of 0 there, meaning it had a horizontal tangent, but it was increasing here and then decreasing here. If f behaved like that, then it would have a local maximum. That means f prime should behave like this. It needs to be positive and then 0 and then negative. And this just doesn't have one, does it? So if it had done this, then it would have a local maximum right there at -5. But it doesn't do that. So it has none of these are the answer. Not only were none of those the answer, it didn't even have one. This one will have some. If I am to consider the graph of f prime, find all the points where f has a local maximum. All right. So it's like we said, if my derivative function could make a line chart that looked like this, then it would have a local maximum. So it's got a local maximum right here at -4 and at -1. Because those are both the places where it's 0 right at -4, but it's positive to the left of -4, and it is negative to the right of -4. It's positive to the left of -1, it's negative to the right of -1, so both of those, -4 and -1, are where it has a local maximum. Determine the local extrema using the first derivative test. All right. First derivative test is just us taking the derivative, putting it equal to 0, and making that sign chart. So t prime would be 3x squared minus 30x plus 48. It has a GCF of 3, so I'll factor that 3 out, and I'm left with x squared minus 10x plus 16. There's our factorization. So it would have a line drawing It's got these two critical values. The critical values are 2 and 8. If either of those numbers went in for x, the result would be 0. So here's 2 and here's 8. And that means that 0 happens over here. And 0 is the easiest number for me to check. If I put a 0 here in the original equation, then I can see that it's just going to be positive. And since these are all unique, it's just going to alternate back and forth. And the consequence here is that t would be increasing and then decreasing and then increasing, and it makes a horizontal tangent at each of those, so it has a local maximum at 2 and a local minimum at 8. Okay, here's another one. Let's find h prime. H prime will be a minus 7 x squared plus 28x plus 147. Now, I'd bet money that 147 is divisible by 7, sure enough. So I'll factor out a GCF of minus 7 and be left with x squared minus 4x minus 21. Then this would factor like minus 7 times let's see, so we'll have a 3 and a 7, and the 7 will be negative, so it's x plus 3 and x minus 7. Well, then my critical values are negative 3 and 7. And 0 is right here in between those two, and if I put a 0 in the original function, it would be positive right there. And because these are both unique, then it's just going to alternate back and forth. So consequently, h has a minimum at minus 3 and a maximum as 7. It has a minimum at minus 3 and a maximum at 7. All right, that is everything for this part 1.